Stefan, thank you very much for your kind introduction and thanks for having me. I am Matthias Arnold, the CTO of the LETS OPC UA companion specification, which will hopefully be released this fall. LETS is an acronym for Laboratory and Analytical Device Standard. In the next 20 minutes I will give you an example of how you can unleash the power of LETS OPC UA and laboratory automation by leveraging the great ecosystem of OPC UA. What are we trying to achieve with LETS OPC UA? We aim for true plug-and-play integration of lab and analytical devices along the laboratory workflow. Seamless connectivity of devices with an absolute minimum of configuration, if any, covering use cases such as monitoring and control, workflow orchestration and asset management. We are aware that it's hard to get this right. Just imagine the large number of different instrument types that need to be considered. This slide gives you an idea of different instrument types which we modeled utilizing LETS OPC UA. The information models were created and most of them even implemented during our workshops and our hackathons. By the way, my colleague Matthias Schuh will give a great talk about our LETS hackathons on Friday of this year's OPC Day International. Let's now turn our focus to lab automation. There are many reasons to increase the level of automation. Better reproducibility of processes, improved data integrity, increased efficiencies, automation of tedious operations, and last but not least, the valuable and limited resource of human operators can be focused on higher value tasks. However, upon closer inspection, one realizes that most equipment was designed not with automation in mind, but for the manual operation by human operators. So we are faced with a challenging situation. Automation of workflows based on instruments which were not initially designed for automation integration. High flexibility, since laboratory workflows change often. Close collaboration with human operators. These requirements call for the integration of collaborative and mobile robots into laboratory workflows. When attending trade shows and conventions in the laboratory and analytical domain, when talking to end users, automation with collaborative and mobile robots is at the top of the list, along with connectivity, fair data and machine learning. Here are some typical examples. A cobot on a lab bench picks up plates and places them in another instrument. Next to him, in the background, a cobot ready to do some liquid handling tasks. A cobot positioning conical vials containing samples in the rotor of a lab centrifuge. A mobile robot that picks up, transports and places labwares with samples, reagents or media throughout the laboratory. As illustrated, supportive robotic solutions are becoming increasingly important for life science and laboratories. The Laboratory Automation Plug-and-Play framework, short LAP, initiated by Adam Wolf of Takeda, aims to provide a blueprint for the integration of such robots. It outlines a hierarchical decomposition of the workflows, the corresponding layers of the control architecture and suitable information representations models, including relative spatial locations of all affected elements in the lab. Some illustrative images from one of his publications. A cobot on a laboratory bench transferring plates. A mobile robot performing pick, transport and place throughout the laboratory. To achieve teaching-free robot integration, the lab concept requires defining geometric position for labware handover and other robotic actions for each instrument. In a best-case scenario, this information is directly provided by the instrument or its digital twin. Unleash the power of the OPC ecosystem. The OPC UA companion specification for robotics. Here you go. The OPC UA companion specifications for relative spatial locations. It provides the geometrical definitions of things like an instrument, the relevant attachment points and relationships of those. This is exactly what is needed to create the best case scenario. Just compare the images and you will see how well they match. Implementing this companion specification in a Let's OPC UA enabled instrument turns it into a laboratory automation plug-and-play enabled instrument. A great example of the synergies you can achieve by leveraging the OPC UA ecosystem. To better illustrate how this works, we simply integrated the relative spatial location companion specification into our Let's proof of concept software and added a 3D visualization to build the virtual robotic enabled Let's OPC UA laboratory. The entire scenery, including devices, their process values, set points, states and geometrical positions are automatically generated and controlled based on the OPC UA information model. Here we are in the virtual Let's OPC UA robotic laboratory. As you can see, the companion specifications for Let's OPC UA and relative spatial locations are placed on the benches. So let's zoom out and look around what we can find in this lab. An assortment of different lab instruments like mixers, centrifuges, work table incubators, plus 2 freezers at the wall in the back. Obviously, the instruments are operated by some invisible ghosts, maybe robots. All of them running, all of them exposing their actual status, including set points and process values, via OPC UA. This information can be viewed on the instrument displays. Within the next minutes, we will focus on the work table incubator. This incubator provides controlled process conditions for cell cultures such as temperature, oxygen concentration, carbon dioxide concentration, and is able to accept up to 4 96 well plates, a very typical labware format. Each 96 well plates will be placed in one of the 4 drawers. A typical operation is picking up a plate once the incubation is complete and its transport to another location for further processing. The drawer opens and exposes the 96 well plate. The current position of the 96 well plate itself and its attachment points for the robot gripper are represented by the green spheres with their colored exits. Each green sphere in this scenario represents a relative spatial location object in the OPC UA information model or one of its attachment points. An invisible robot lifts up the 96 well plate, moves it away, and transports it to another location in the lab. The empty drawer closes and waits for the next plate to be inserted into. After a while, another invisible robot approaches with a new 96 well plate to be incubated. The drawer opens, exposing the position where the plate should be placed. The robot inserts the plate at that exact spot, and the drawer closes. How does this look like from an OPC UA point of view? The relative spatial location object representing the 96 well plate is currently linked to the drawer object. Its so-called position frame defines its geometric position in relation to its parent object. The parent object is defined by the base property. Due to the design of the incubator's drawer, the 96-well plate must be turned about 90 degrees about its vertical axis to be placed in the drawer. This is represented by the orientations property B, which is set to 90 degrees. The plate's position relative to the drawer is defined by the properties X, Y, and Z. The robot can derive the attach points where it places its gripper from the corresponding definitions in the attach points list. For example, the X position of the left attachment point is minus 6.3 something centimeters away from the plate's center. I think we can all agree that it's much more convenient for us human beings to see the results of all this data processing in the virtual 3D scenery, rather than looking at the raw data in the information model. But that's how it actually works behind the scenes. While the incubator we have just inspected is one of the few lab devices designed with automation in mind, we will now turn to another typical lab device which is designed for manual operation. A laboratory centrifuge, one of the most common laboratory instruments. Its lid is currently opened, exposing its rotor. The green attachment points define the positions where labware should be placed. Please note that the positions are inclined with respect to the rotor's vertical axis. This is very important information whenever a robot wants to place or pick a labware like a conical vial in the rotor. Whenever stopped, the rotor itself can be oriented in any angle to the centrifuge's cabinet. This is illustrated by the additional attachment points on the outer circumference of the rotor, which is intended to serve as index mark. Looking at the position frame of the rotor object, we learn that the rotor has stopped at an angle of 330 degrees. In the attachment point list, one can find the position of each individual sample position, including its tilt angle. Since the device was not designed with automation in mind, the robot might even have to operate the user interface elements. Some examples. By pressing the lid button in the upper left position of the front panel, the lid is closed. The robot can perform such an operation if the button's position is also defined by a relative spatial location object. By turning the lower right dial, the speed set point for the next run can be defined. Again, the corresponding relative spatial location object is a great help. By pressing the Start-Stop button in the upper right position, the centrifuge run can be started. By leveraging the power of the OPC UA ecosystem, we can achieve the remarkable goal of teaching free laboratory automation plug and play, even with equipment that was not initially designed for automation integration. In the future, laboratory automation can take a big step forward thanks to the OPC UA ecosystem with its diverse companion specifications, covering, among others, laboratory and analytical devices as well as robotics. This opens up exciting possibilities, empowering laboratories with enhanced efficiency, improved workflows, and streamlined operations. The future of automation in the laboratory is within reach, and the OPC UA ecosystem is leading the way. By the way, did I mention that cloud connectivity is an important use case in the laboratory and analytical domain as well? And as you all know, the OPC UA interoperability standard provides a solution for this requirement. Stefan Hoppe visited us during our fourth hackathon, which took place in Berlin at the end of March this year, just 3 weeks ahead of Hanover Fair. During his visit, he asked whether some participants of our hackathon, most of them still very new to the world of OPC UA, wanted to participate in OPC Foundation's UA Cloud Showcase presented live at Hanover Fair. This really resonated and the outcome was great. Some integrated OPC UA PubSub directly into their device software. Others utilized UA Cloud Publisher as edge gateway to push data to the cloud. In the end, we were happy to populate the OEA Cloud dashboard presented at Hanover Fair with live data from our laboratory and analytical devices. And, yes, of course, the Let's OPC UA virtual laboratory that I introduced during today's presentation also uses OPC UA PubSub to publish selected instrument data and status all the way to the cloud. Just watch the sensor signal from the balance as you weigh a series of samples. See the temperature inside the centrifuge compartment rise to ambient temperature as soon as the lid is opened, and so on. OPC UA stands as the unparalleled champion of industrial interoperability standards, boasting a track record of proven security. OPC UA serves as the foundation for digitalization and extends its transformative reach across industries to laboratories. Thank you very much for your interest in Let's OPC UA, the laboratory and analytical device standard. I'm happy to receive your feedback, discuss your comments, and answer your questions.